Welcome to our video on bolus patient side surface design using P.D. So as you can see, I have P.D open. I have my ECT nose case provided by .decimal loaded into the software. If you have any questions regarding loading the patient into the software, please see the video tutorials dedicated specifically to that section. Also, when loading in the patient, I use the .decimal example machine. So if you have not set up that machine yet in your system, please view the video on that to help you set up your machine in P.D as well. So we're going to begin with the bolus wizard. And what we're going to focus today on is the patient side surface. So we have to design the patient side surface whether we're doing an optimized thickness bolus or whether we're doing a flat top bolus. Because I want to illustrate a few of the parameters that are specifically kind of more important to the optimized bolus, we're going to go ahead and stick with this option today with the optimized bolus. So the machine selected for me is the one that I selected with my plan, the .decimal example machine. I'm going to keep my 120K scanner. I'm going to keep all the defaults here for all of these because they're not going to affect my patient side surface calculations. All right, except for the external. Okay, the external is what my patient side surface is actually going to fit. So we need to make sure that we select the appropriate structure here for our patient side surface. In this case, there's only one set of external contours for the patient, and it is called external. I also need to make sure I select the correct target. And the reason we need to select the correct target is because P.D determines the depth to go with the bolus in the CAX direction based on the target. So I'm going to go ahead and make sure I select my correct target. For this particular plan, we want to use the nose target. Okay, this beam, the nose is the only target volume that's really lined up with our beam here. These other ones were designed for a secondary beam in another case. So select your external body, select your nose target, and then let's go ahead and move on to our surface page. So on the surface page, we have a few parameters here. The block outer border, the unmilled margin, the depth beyond target, the point spacing, and then whether or not we want to utilize rolling ball smoothing. And we're going to discuss each one of these parameters as we go through our tutorial today. Okay. If we notice here, I just pulled up the help page. The way that I pulled up this help page, anytime you're in P.D software, if you click the F1 key, you can pull up this context-sensitive help. So if at any time you forget what any of these parameters mean, okay, rather than watch this whole video again, you can simply pull up the help page by clicking F1 on the appropriate page, and you will see the P.D help appropriate to that topic is pulled up for you. Okay, so in this particular case, we're looking at the distal surface page. It reminds us what the block outer border is, reminds us of the unmilled margin, the CAX, the depth beyond target, which is in the CAX direction. If these details aren't quite enough, there's also a link in here to get us to the actual technical specifications that'll give us some more details regarding these different parameters. Okay, so we see some images of these parameters that help to define them a little bit more clearly. So we'll discuss them as we go through today as well. So remember, anytime you are within a wizard, anywhere you want to be, click F1 and it will pull up that help for that particular option. So if you forget what any of these mean somewhere down the road, haven't used P.D in a couple months, remember the F1 key will be your friend in finding information regarding those topics. So let's see if we can kind of explore the effects of these different parameters, and that's really going to help us understand what they are and what they mean. The last one here, the depth beyond target, is actually going to be kind of the most straightforward one to understand and visualize. So let's just go ahead and make a surface real quick with the default values and see if we can understand this depth beyond target. Our surface here showed up in white. I'm going to zoom in a little bit more. Okay, so we can see here where our bolus stopped. Okay, and if we go up to a couple slices where the tumor is, if we kind of find the deepest spot on the tumor, somewhere about in here, okay, that's the deepest that our tumor ever reaches, is about right here where my mouse is. And notice the bolus will stop about a ½ centimeter beyond that. That's what the depth beyond target is. Well, for this particular plan, that doesn't seem to be too bad most of the way through this. But as I get close to the eye of the patient, we're going to notice that that depth beyond target isn't quite enough to fill in this gap. Okay? And well, if this eye is inside the treatment field, which maybe I can see from the 3D view, so if I look down the axis of my patient, we're going to see that, well, maybe the edge of the patient's right eye might just be in the treatment field. So I might want to make sure that I have bolus all the way down to that patient's eye, because it's going to help protect and reduce the level of dose that's seen in that eye. So for this particular case, the default value of 0.5 centimeter probably isn't enough. Okay, I'm going to make sure I at least go that far. Maybe I even want to go a little farther, maybe to 1.5, just to make sure that it gets down into that region. And there we go. We see now the only spot we have any, we have even reached our depth beyond target limit is right over here to the patient's left side. Everywhere else we're actually contouring and fitting all the way to the patient, because the patient surface is within that 1.5 centimeters everywhere where the bolus is defined, except this little region here. All right, so my patient surface looks pretty good now. All right, so that is our depth beyond target value. All right, so let's see if we can grab a quick understanding of these other two properties. Now, the block outer border and the unmilled bolus margin, they're kind of difficult to see the effects of them on the surface page alone. I'm going to make this value small again just so we can kind of see their effects a little bit. I want to be able to see the end-to-end size of my bolus. So if we look here, we can kind of see the two edges of the bolus. And we're going to notice if I make this 1 centimeter larger, the unmilled margin, my bolus is going to grow by 1 centimeter, okay, in each direction. There we go. If I make my block outer border 1 centimeter larger, okay, I'll put this back down 1 centimeter. We're going to notice it's not going to change. It's going to be the same exact size it was a moment ago. And the reason is both of these parameters will increase the overall size of our bolus, the horizontal size of our bolus, okay, in the plane perpendicular to the CAX. So both of these parameters increase the size of the bolus. It's where they increase the size that's different. So I'm going to leave the settings like this. Bring this guy back to make sure he goes all the way down into that eye. And then I'm going to go ahead and generate my surface. And just so we can see the effects of these two, I'm going to generate the actual bolus too. So I just want a very quick bolus generation, so I'm just going to use a geometric sequence here. Click Generate so that I can see what the bolus looks like, and we can kind of explain what these parameters do. I'm going to go ahead and switch to 3D view here. And I'm going to turn my beam off to get it out of the way. Maybe turn my block off for a second too. All right, so what we can see here is the 3D view of our bolus. And what I want to point out is this flat area surrounding the edge of the bolus here. This flat area is called our unmilled region. So our unmilled margin is the minimum distance that P.D is going to allow from the actual modulated region to the edge of our bolus. And we see that we've got that set, if we go back, we've got that set at 1 centimeter right now. So we have 1 centimeter between the edge of our bolus and the actual edge of the modulating surface. Now the block outer border, on the other hand, that defines, and I'm going to go turn my block back on. Okay, our block outer border is going to define the distance from the projection of my block. So if I were to project this block down to isocenter, okay, that's going to define the distance from that projection to the edge of the modulated region. That is our block outer border. So we see that when we look down the beam's eye view in this case, the modulated surface is very big. I can almost see it all the way on the outsides of my block. And that's because I have such a large block outer border. That's 2 centimeters from the edge of the block to the edge of my start of my unmilled margin, or my unmilled region. So let's switch these parameters and see their effect. So I'm going to go to 2 on my unmilled margin and 1 on my block outer border, and we're going to see that the overall size of the bolus won't be affected by this because I decreased it by a centimeter and increased this one by a centimeter. Regenerate my surface. Reconstruct my bolus real quick. And we're going to see the drastic difference in the appearance of the bolus. Notice now, okay, we have a 2 centimeter, I'll go back a page, we have a 2 centimeter unmilled margin. So the distance from the edge of the bolus to the modulated region is now 2 centimeters, and the distance from the projection of our block to the edge of our modulated region is only 1 centimeter. So we see this cutout region, this actual milled region, got much smaller. It got a centimeter smaller in all directions around it. So typically the block outer border, you'll see the default value is 1 centimeter. Typically we don't need much more than 1 centimeter. The only time we would need to increase this value is if we have a very large SSD and our field is very divergent. We might want to make sure that, well, as we project from the block cutout from isocenter down to our bolus, we want to make sure that we don't get out into that region. So if you have a very large SSD for a patient, we may want to increase this block outer border a little bit. But in most cases, a ½ centimeter or 1 centimeter is more than sufficient to make sure that our treatment field is not hitting any of these sloped walls. And that's basically the sole purpose of the block outer border, to make sure that the treatment beam does not hit these steep sloped walls and funnel the electrons down and create a hot spot in our patient field. Okay? So block outer border just keeps that sloped wall out of our actual treatment field. The unmilled margin, there's typically very little reason to change the unmilled margin. You'll see the minimum value that P.D allows is 1 centimeter. That's the minimum region or size that we need at dot decimal to include the patient-specific engravings that we need on our part to make sure that you're using it for the right patient, to make sure that we're sending you the right part, and to keep track of these parts when you have them at your facility. So the unmilled margin, the only reason you may ever need to increase that if you want a little bit larger bolus, if that's going to improve your ability to fixture it, your ability to hold it to the patient surface, you may want to increase that in some cases. So if you have any particular reason to specifically increase the unmilled margin, that is the purpose of it, just in case anyone wants to change it. There's probably very few reasons other than maybe it helps in fixturing in certain cases, depending on the angle of the patient. Maybe the bolus can just sit right on the edge of the table if you're treating from a horizontal beam position. Okay? So that is our 3 bolus geometry options. The last one we're going to see here is our smoothing. And we can go back to the 2D view to visualize the smoothing. Just generate a new surface real quick. We're going to lose all our previous results. That's what that warning is, which we're okay with. All right, so we want to take a look at the smoothing options now. And the reason we may want to smooth the surface, we see in this case that, well, there's obviously some kind of mask that was used to immobilize this patient. So because of this mask, our patient contours may not be very good if we auto-generated them in our treatment planning system. So sometimes with the mask, we see kind of oscillations or a little bit of noise in the patient side contours. And that's what the rolling ball smoothing can kind of help take away sometimes. And you'll see things like this, where on this particular location on the patient, it actually looks like the bolus surface would be protruding into the patient. So obviously we're going to have an interference here. This bolus may not fit on the patient if we allow this to be here still. So depending on whether this is an artifact in our scan or in our contour, or whether that's physically there, that's going to tell us whether or not we need to worry about this. You'll know that for your actual patients. But if you have any issues, any noise, any problems with your patient contours, sometimes the rolling ball smoothing can help fix those. So this is a pretty small case. Typically you're going to want to use a small radius, especially for nose cases like this one. We'll see that when we apply the rolling ball smoothing, the effect of this is basically if we rolled a ball along the surface, it's going to try to eliminate any peaks any valleys that are seen as we roll a ball along the surface. Well, that also has the effect of lifting the surface slightly off of any surfaces that are inclined nearly parallel to the beam. So with nose cases, we see that the slope of this nose is very close to the slope of our beam along that direction. So when we generate this surface, we're going to see that, well, the surface kind of lifts off these steep slopes on the nose here. And we can actually create a pretty large cavity. While in this direction, that air gap is pretty small. But remember, the beam is going to be slightly divergent. So in a ray of the beam, some of the electrons may see a pretty large path in this air. So that may be unacceptable for a lot of nose cases. You may either need to use a very small smoothing radius, or you need to make sure that you do not apply rolling ball smoothing to many nose cases. On chest wall cases where patients are very flat and the patient surface is very perpendicular to the central axis, the rolling ball smoothing can do a great job of eliminating some of the noise in the contours that you may see. But for nose cases, we need to be careful of the gaps that result from this rolling ball smoothing. Okay, but we see that it did eliminate this area where the bolus was going inside of the patient here. Okay, we see what appear to be a lot of air gaps, and the reason is remember, this is a 3D algorithm. This is a 3D patient, and we see the contours kind of jumping back and forth in 3D. We see the nose growing here in the anterior direction, and the rolling ball is just getting as close to the surface as it can in any of those particular directions at any time. So we do get some gaps for surfaces that are not smooth in all directions. We see along the chin surface here, we're getting pretty good fit here because we have a pretty flat surface in this direction. Okay. The other thing I want to point out is the point spacing. And the point spacing will affect the length of calculation time for the patient side surface. So as we increase the density of the points, we're going to take a little bit longer to calculate the patient side surface. That's especially true when we apply rolling ball smoothing. The rolling ball smoothing will increase the computational effort quite a bit for the patient side surface. So if you use a fine discretization and rolling ball smoothing, it may take some time for large patients. For nose cases, it's typically pretty small fields, so it's still going to be a pretty quick process. But bear in mind that this will affect the calculation time for the patient side surface. The dose calculations, however, for the optimized thickness boluses will not be affected by this point spacing value. Okay? The dose calculations in P.D, remember, are going to be for reference only. So when you're computing dose in P.D, the dose grid size is determined by P.D. This does not have any control over that particular size. All right? So one last thing we want to look at, if we look at the beam's eye view for this case, and we don't see anything other than the block cutout right now, I need to actually have a patient side surface to do this. So I don't want to use rolling ball smoothing, but I just want to generate a bolus real quick because the beam's eye view is going to help us kind of understand that point spacing a little bit. So I'm going to zoom in on my bolus here. All right, so this shows me a top-down view of my bolus. So I'm looking at the thicknesses. This part is colored by the thickness of the boluses. But if I right-click and I do Show Grid, I can see the actual calculation points that were used to define the bolus surface. So we see the size of a 2 millimeter spacing. It's a pretty small spacing. We have quite a bit of points on this bolus surface. This is going to give us pretty good resolution for defining our bolus. However, if we decide we want to be coarser or more refined, we can always recompute the bolus, and we can see what those effects would be on the resulting bolus. And we'll see even with a 4 millimeter spacing, it gets quite a bit more coarse. Our bolus surface won't be nearly as refined. If we were to look at this in 3D now, we'd see that it looks a lot more stepped, a lot less refined on our surface. We can see that we don't get nearly as nice of curvature across here. So just make sure that the bolus point spacing is appropriate for the size of your patient field. If you have a very large field, 4 millimeter spacing may be perfectly sufficient. If you have a very small field, you may need to decrease that down to a 1 millimeter point spacing. All right, I want to take a look at one last thing here. I'm going to go ahead and cancel this. and open up another patient. So I'm going to open up the ECT chest wall patient. And we'll take a quick look at the rolling ball smoothing on a patient where the beam is relatively perpendicular to the surface. So I'm going to select my defaults again. We'll go ahead and do all the defaults except let's apply rolling ball smoothing with maybe a 3 millimeter radius. And we'll take a look and we'll see that the rolling ball smoothing does a very good job of kind of smoothing out a few of the highs and lows. We've got a small little valley here in our patient surface, kind of smooth that out for us. If we look at the sagittal view, we can often see that, well, along the contours of the patient, because remember this is perpendicular to the direction that you contoured, a lot of the bumps that result from a little bit of inaccuracy on the per slice contours, we can see a lot of those bumps get smoothed out by the rolling ball smoothing process. So it takes a lot of the variation across contours out of our patient bolus surface design. So the rolling ball smoothing on a chest wall case can be a very good option to help eliminate some of those variations along the contours. Okay, I hope that gave a good overview of all of the options available when creating a patient-side surface. Remember to keep in mind the goal of the patient-side surface. We want to create a nicely fitting surface that's not going to be uncomfortable or cause any physical discomfort for the patient, but we also at the same time need to minimize any air cavities or air gaps that exist between the bolus and the patient, because those can increase the skin dose that is seen at the patient. All right? So keeping those in mind, try using the different parameters, applying smoothing when necessary to create a bolus surface that matches as best we can.